Once you've learned to draw the Lewis diagram for a molecule, it's important to start looking at what its three-dimensional shape will be, because that has some impact on its behavior. The theory that we're going to use is called VSEPR Theory, and those letters, VSEPR, stand for Valence Shell Electron Pair Repulsion Theory. Now, what does that theory tell us? Well, think about the name. Valence shell electron pairs repel other electrons. You know that negative electrons would repel other negative electrons. So this repulsion by these outer shell electrons causes the molecule to bend and twist in a way that gives it a three-dimensional shape. Now in this presentation, I'm going to show you an example of each one of the geometries, and you're going to have a chance to look at the shape, think about the types of compounds that would have that shape, and look at the properties with the bonding. So let's get started. The most simple shape of a molecule is linear. The formula for a linear molecule can be A2 or AX, where A and X are just some generic elements, or it could be 3 atoms in a molecule, AX2. You see over here on the left side, I've got all 3 of those drawn out for you. The key to recognizing a linear compound is to see that it has either 1 or 2 shared pairs, no more, and there are no unshared pairs on that central atom. Now if you look at the colored diagram on the bottom left of this slide, the element A is the central atom. You see how there are no unshared pairs there. So because of that, these 2 bonds are going to be as far away from one another as possible, and that's when they are 180 degrees apart. So a linear molecule has 2 or 3 atoms in it with 1 or 2 shared pairs and no unshared pairs on the central atom. One that looks very similar to linear is bent. Now the formula for a bent molecule is AX2, so you have 3 atoms in the formula. There are 2 shared pairs in this diagram. The main difference between linear and bent is that this bent molecule has an unshared pair on the central atom. This particular diagram has 1 unshared pair, but if there were 2, it would still be a bent molecule. The reason that that happens is that unshared pair repels those shared pairs, and that repulsion causes the bonds to bend away from the unshared pair. That makes the molecule a bent configuration rather than linear. The third geometry we want to look at is a little bit bigger. It's a molecule that has the formula AX3. A is the central atom, and there are 3 bonded elements on the sides. This molecule has 3 shared pairs. If you look on the central atom A in the diagram, there are no unshared pairs on the central atom. So these bonds arrange themselves symmetrically and as far away from each other as possible. If you think about this molecule and the X's arranged in a circle, the angles here are 120 degrees because that equally divides the 360 degrees that they have to take up space. Trigonal planar is very similar to this next structure, Trigonal Pyramidal. The formulas are the same, as a matter of fact, AX3. But you see the difference here is that there is an unshared pair on that central atom A. That unshared pair causes those single bonds to be pushed downward, and the molecule goes from being planar or flat to being pyramidal, shaped like a pyramid. Now this diagram is a little more complicated, but basically what you're looking at is a 3-dimensional structure. The 2 red triangles represent single bonds that are coming out of the screen towards you, and the white triangle represents a single bond going back into the screen away from you. So Trigonal Pyramidal does have a central atom with 3 attachments, but there are unshared pairs. Now this molecule is larger again. Tetrahedral, think about the prefix tetra, and it means 4. This molecule has a central atom with 4 bonded attachments. There are 4 shared pairs in this molecule. There are no unshared pairs on the central atom. Now if you look at the way this one is set up, the 2 red triangles represent single bonds coming out of the screen, the white triangle represents a bond going into the screen away from you, and then the top X has a single bond that is in the plane of the screen. In three-dimensional shape, this looks like a tripod with a camera standing on top of it. But remember that tetra means 4, so this is a molecule with a center and 4 shared pairs. Let's look at an even larger molecule. This one is called Trigonal Bipyramidal. Now trigonal refers to 3 and bipyramidal refers to 2. 3 plus 2 is 5. So this molecule has 5 shared pairs. If you notice the central atom A, there are no unshared pairs on this one. So Trigonal Bipyramidal has this shape. The central atom A has 3 bonds in the plane of the A. There's one bond coming straight up from the A in the center, and there's one bond going straight down. The final shape is octahedral. The formula for this one is AX6. A is in the center, and there are 6 attachments. Now, the last one, Trigonal Bipyramidal and octahedral, actually break the octet rule. Some atoms can do that. In octahedral, you're looking at 6 shared pairs, so the central atom has 12 electrons around it. There are no unshared pairs on the central atom. The way that this one is designed, the A in the center has 4 X's bonded to it with single bonds. 2 are going into the screen and 2 are coming out of the screen. So it's almost like they make a square shape. The 5th bond is straight up from the A, and the 6th bond is straight down from the A. So those are all of the geometries. What you need to keep in mind is looking for the central atom and looking for unshared pairs there. If there are unshared pairs, it's going to affect the geometry. You need to practice memorizing these and learning what to look for in a formula when you decide that shape.